Now let us look at acids that have several protons available for dissociation. Examples. Phosphoric acid, H3PO4, has 1, 2, 3 protons. For phosphoric acid, they are identical. That dissociate at pH 2.14, pK1, at pH 7.119, pK2, and at pH 12.32, pK3. Carbonic acid has 2 protons that dissociate in acidic area and in basic area step by step. Tartaric acid has 2 protons, 2 carboxylic groups, this and this, dissociate at 289 and 440. These, and these protons never dissociate in aqueous solution. A more complex example is pyridoxal phosphate, active form of vitamin B6. It has proton that dissociate at 1.4, first proton dissociate, then phenolic proton at pH 3.4, and then second phosphate proton at pH 6, and the last will be protonation of pyridine nitrogen at 8.5. So we have 1, 2, 3, 4 pKs for this compound. All amino acids have several modes of dissociation. Now, amino acid has amino and carboxylic group, but it never exists in this form. The real form is so-called Zwitter ion. So positive ammonium group and negative carboxylic group, both of them are ionized. Total charge, of course, is 0. Let's look at one of the simplest amino acids. In acidic solution, it will have protonated carboxylic group and protonated amino group. Now, first pK is 235. So at pH 235, our compounds will undergo deprotonation of carboxylic group and become neutral amino acid with carboxylic group negative and ammonium group positive. Second pK is 987, and here we have complete deprotonation of both groups. So we have amino group and carboxylic ionized group. This is common behavior for all amino acids, and as a matter of fact, all proteins. Just example, we just look at alanine, simple CH3 substituted amino acids, and we had carboxylic pH 2.3 and ammonium 2H6. With arginine, we have more acidic carboxylic group, more acidic ammonium group, and one more substituent group here. Aspargine, again, 2 substituent group. With aspartic acid, we have 2 carboxylic groups, because our substituent has carboxylic group, so we have 2 of them, and we have ammonium. Cysteine with SH group can dissociate at 836 here. Glutamic acid, again very famous, has two carboxylic group and one ammonium, and so on. Now let's look how we can calculate pH of solution of this species. Let's consider a very important example, that is carbonic acid. pH of carbonic acid itself, we already were talking about it. It's solved as any weak acid. We use K1 and put into calculation the concentration of carbonic acid, and we have pH. It's any weak acid. For completely deprotonated carbonate, say sodium Na2CO3 soda, you have carbonate ions in solution which are weak base. As any weak base, we'll use this second constant as we did for phosphate before and calculate pH of this solution. It will be very basic. Now, what about intermediate form, hydrogen carbonate? This is so-called baking soda. This is laundry soda, strongly basic solution, and this is baking soda, hydrogen carbonate. So again, we have three forms: carbonic acid itself, hydrogen carbonate, and carbonate ion. We have constant number 1 and constant number 2. The fact that it is sodium salt doesn't matter, because sodium hydrogen carbonate dissociates completely 100% into sodium ion and hydrogen carbonate ion. Now, how can we calculate pH of this solution? For doing that, we'll do some algebraic trick just to have an equation. We'll multiply constant 1 by constant 2, K1 by K2. So I'm multiplying this expression by this expression. So here and there, this. What I have, above the line and below the line, I have same HA. Now, I have H plus here and H plus there, so I have H plus square A by H2A. Let's consider, when I have pure hydrogen carbonate, to make one carbonic acid, I need to take proton from somewhere. So the only species I can take it is hydrogen carbonate itself. So by making one carbonic acid, I am making one carbonate. By making one carbonate, I am making one carbonic acid, which means these two concentrations are identical, just from stoichiometry. So this and this is the same. As a result, I have H plus square multiplied by K1, K2, or taking a square root, concentration of hydrogen ion is square root of first constant multiplied by second constant. Now, if I'll take log of this and take negative sign, I'll have, instead of concentrations, I'll have pH, pH, pK, and pK. pH is pK1 plus pK2 divided by 2. Very simple formula. This is not an exact formula. We did lots of approximations, but this is sufficient for our purpose. So we have pK1 635 and pK2 1033. Taking average of these two, I have pH 834. What's interesting, this number is the same for any concentration of hydrogen carbonate, as long as it is high enough. Low concentrations, of course, will make deviations from this equation. But for anything above, say, 10 to the negative 1 molar and above, we'll have approximately the same result, 8.34. pH of sodium hydrogen carbonate, as well as pH of any compound like this, will be independent from its own concentration.